In episode 1, we kept things simple. One switch, one cable, one bad idea. We saw how a layer 2 loop can cause broadcast storms, MAC address flapping, switch CPU problems, and can cause a very bad day for anyone who enjoys having a working network. But now, we are going to make things a little more realistic, because in the real world, we usually don't have just one switch. We have multiple switches, multiple VLANs, multiple links, and once VLANs enter the picture, spanning tree gets a little more interesting. Today, we're talking about per VLAN spanning tree and rapid per VLAN spanning tree, or in human language, a separate spanning tree topology for each VLAN. What's going on, everybody? Welcome back to the Panic Room. This is episode 2 of the spanning tree series. In episode 1, we focused on basic spanning tree and basic rapid spanning tree behavior on a single switch. We covered what a loop is, why it's dangerous, what BPDUs do, and how spanning tree places ports into forwarding, blocking, or discarding states. In this episode, we are expanding the lab. We're going to use 2 switches, 2 trunk links, multiple VLANs, and we're going to see how Cisco can run a separate spanning tree instance for each VLAN. The main goal today is not to build some massive enterprise topology, not quite yet anyway. That's coming later. Today, we're staying in the middle. Not just one switch anymore, but not a full core access layer type design either. We're going to focus on how per VLAN spanning tree and how rapid per VLAN spanning tree behave when multiple VLANs are writing across multiple switch links. Before we get going, I just want to clarify one thing. So in the book, you're going to see PVST plus and rapid PVST plus. All that means is literally per VLAN spanning tree plus and rapid per VLAN spanning tree plus. Now, the plus, all that means is it's an enhancement on regular spanning tree and regular rapid spanning tree. So as you know, spanning tree does take a little bit longer to do its convergences, while rapid spanning tree is faster. It's all the same. It's just they enhanced it a little bit to make it a little bit better. But from here on out, going through this video and everything I've written down, I don't want to keep saying per VLAN spanning tree and rapid per VLAN spanning tree because it's a mouthful. So I'm probably just going to reference it as spanning tree and rapid spanning tree. Just wanted to throw that out there so you guys can follow along, but also understand the concept trying to go behind here and just not say a bunch of extra words during all this. Thanks for that. So before we talk about spanning tree, I just want to throw something out there real quick. I want to just go over and simplify what a VLAN is. Some people might be jumping into the series right in the middle. Could be somebody new to networking, so it never hurts to really just go over terminology. A VLAN is basically a separate layer 2 network. So when someone says VLAN 10, VLAN 20, and so on, they're actually just talking about separate networks. For example, your VLAN 10 just might be for your users. VLAN 20 might be your server network. VLAN 30 could be for printers. VLAN 40 for voice. Very common to separate out different types of traffic. And most of the time, each VLAN maps to its own IP subnet. A lot of small and medium networks, you will commonly see /24 networks, right? So your subnet mask is 255.255.255.0, and that just leaves 254 usable addresses. So your VLANs may line up where VLAN 10 is, we'll just use easy numbers here, 192.168.10.0/24. VLAN 20, 192.168.20.0/24. A lot of places like to line up usually the third octet in your range. That doesn't mean every VLAN has to be a /24. It's just common design because it's easy to understand and easy to manage. So just remember, for this video, when I say VLAN, you can think it's just a separate layer 2 network. And when we talk about spanning tree, we're talking about Cisco running a separate spanning tree topology for each one of those VLANs. Let's go over what per VLAN spanning tree stands for. It literally stands for per VLAN spanning tree plus. The name actually explains the concept pretty well. Per VLAN. That means each VLAN gets its own spanning tree instance. VLAN 10 can have its own root bridge, its own root port, its own designated ports, its own blocking ports, and its own forwarding topology. Then VLAN 20 can have its own root bridge, different port roles, and different forwarding topologies. The physical switch will be the same, could be the same. The trunk links are probably going to be the same. The cables are probably going to be the same. But it's the logical forwarding decisions by that switch that can be different per VLAN. That is the big concept for this episode. Per VLAN spanning tree doesn't create one spanning tree topology for the entire switch. It creates a separate spanning tree topology for every participating VLAN or network. Now let's separate the two terms that are easily blended together. Per VLAN spanning tree and rapid per VLAN spanning tree. Spanning tree uses traditional spanning tree behaviors per VLAN, whereas rapid spanning tree uses rapid spanning tree behaviors per VLAN. So both are per VLAN. The difference is the underlying spanning tree behavior, where just regular per VLAN spanning tree is based on traditional spanning tree, and same with rapid spanning tree per VLAN, rapid spanning tree behavior. We know that rapid spanning tree generally converges faster. It uses rapid spanning tree concepts like alternate ports and discarding states. The most common Cisco environments use rapid spanning tree. You'll see that in most organizations or most labs, and you can actually easily verify that. All you need is to do a show spanning tree summary, and if the switch is running rapid spanning tree, you'll see something like switches in rapid PVST mode. Easily configurable. To configure rapid spanning tree, the command is simply spanning tree mode rapid-PVST. And for traditional per VLAN spanning tree, the command is just spanning tree mode PVST. But do not just casually change spanning tree mode on any type of production switch. It's actually a global setting, and it will definitely affect your network. So lab it up first, understand it, and then make intentional changes. I'll give you a quick overview of the lab setup today. I'm going to be using Cisco Packet Tracer just because it's going to get the job done for the demo. I definitely like JNS3 more, but for the sake of time and ease, we'll just bang it out in Packet Tracer today. So I'll be using two switches labeled switch A, switch B. Between the switches, I have two separate trunk links. Both trunk links are carrying VLAN 10 and 20. These are configured just as trunks, not as ether channel. That part matters. If we bundled the links together with ether channel, the switches would just treat both physical links as one logical link, which is quite normal. But for the demonstration, we just want two separate paths. Having two separate paths like that creates the risk for a loop, and that gives spanning tree something to block, something to demo. Alright, let's jump into the demo real quick. I'm recording this after the fact, so bear with me if it doesn't fit in perfectly. So right now, I have switch A and B with redundant links. I have PC1 and PC2 both in VLAN 10. I have PC2 pinging PC1. I will pull it up right now. Physically, there are two cables connected to the switches, but technically only one of them is forwarding traffic. On switch B, let me get over there. Oops, we timed out. One moment. Let me just do a show spanning tree VLAN 10. We'll do the same over here. Alright, as we can see, switch A is the root. But what I wanted to show you was on switch B, we can see that port 24 is in alternate and it's blocking. So what I'm going to do on switch A is I'm going to shut down FA023 because right now it's doing all the forwarding of all the traffic, and I want this to converge so you can see what actually happens. So let's just do that real quick. All right, here we go. Shut. Okay, we can see it shut down over here and shut down over here. But we're not losing any pings. So let's figure out why. Show spanning tree VLAN 10. Show VLAN. Nope, show spanning tree VLAN. Alright, okay, so switch B jumped to port 24 being the root port, and now it's forwarding. So why didn't we lose any pings? It's because there wasn't a loop at that moment. There wasn't physically the two connections were there, but one was shut down. So the two switches only seen the one link. Now, let's jump back on switch A. Let's do int fast Ethernet 023. Let's bring this port back up. No shut. Okay. That's coming up. And we're losing pings. Now, why are we losing pings? We actually have more redundancy up. Well, at the moment, spanning tree is working it out. So what actually happened is now we have two links connected to the two switches. So a loop could happen right there if spanning tree didn't do its job. And as you can see, it just converged. So that's the big difference on why when we did a shut, we lost no pings. But then we did a no shut and we started losing pings. So that was it looks like 5 seconds of timeout. Now, you probably wouldn't even feel that out in the world. If you're at your desk, you might just think, you know, something's laggy. Users probably wouldn't know the difference, but if they're trying to save something, it might just spin for, you know, about 5 pings. So it definitely came back. I wouldn't suggest just pulling links and doing all this all willy-nilly. Definitely work it out, you know, because what if it didn't come back? And then now you're fighting an actual outage. That's never fun either. So, all right. Let's get back to the rest of the video. Let's talk through why two links between switches can create a problem. Imagine a device in VLAN 10 sends a broadcast frame. Maybe it's an op request. Switch A receives the broadcast. Because it's a broadcast, switch A floods it to all other ports in VLAN 10, including the trunk links towards switch B. Now we have two trunk links, so switch B may receive the same broadcast through both paths. Then switch B floods the broadcast again. That frame can return to switch A floods it again. And now we have the same basic problem from episode 1. Except this time, the switch loop is between two switches instead of just two switch ports. Spanning tree prevents that by allowing one logical path to forward while placing the redundant path in a non-forwarding state. The physical redundancy remains, but the logical loop is stopped. Now, here is where spanning tree becomes more than just loop prevention. Why would we want switch A as the root bridge for VLAN 10? Why not just let the switches figure it out automatically? Technically, they will figure it out, but that does not mean they'll figure it out in the way that matches our design. Let's say this is a small company, switch A has a server connected to it. Maybe that server is heavily used by the users in VLAN 10. In that case, it makes sense for switch A to be the root bridge for VLAN 10, because now VLAN 10's layer 2 topology is centered around that switch where important resources live. The goal is to keep the traffic on the most logical path. If the users and the server are on the same side of the network, there may be no reason for the traffic to take some weird path and go through the other switch, unless it has to. So with per VLAN spanning tree, we can say for VLAN 10, switch A should be root. For VLAN 20, maybe switch B should be root. Different VLANs, different logical topologies, same physical switches. So, to influence the root bridge election, we can adjust the spanning tree priority. Lower priority wins. The easy Cisco command is spanning tree VLAN 10 root primary. That tells the switch, try to become the primary root bridge for VLAN 10. There is also spanning tree VLAN 10 root secondary, which tells the switch, if you're not the preferred root right now, but if the primary disappears, you should be in a good position to take over. You can also manually set the priorities. For example, spanning tree VLAN 10 priority 24,576. The default priority is usually based around 32,768, so setting the lower value makes that switch more preferred. But for a beginner or intermediate type lab, the root primary and root secondary commands are just easy to demonstrate. So those numbers that I was just spitting out, they do actually mean something, and we will go over that when we get into setting priorities a little bit differently in the next episode. Now let's define the main port roles we are seeing. The root port is the best path from a non-root switch back to the root bridge. I know that's a lot. Maybe listen to it again, maybe write it out, but you gotta kind of commit that to memory. The designated port is the forwarding port for a specific network segment. The alternate port is just a backup path. With rapid spanning tree though, an alternate port sits in discarding. It's not forwarding normal user traffic, but it is ready to take over if the active path fails. The root bridge itself does not have a root port because it's already the root. On the root bridge, the participating ports are normally designated forwarding ports. So when you look at the output, do not just stare at forwarding and blocking. Look at the role 2, designated alternate. That tells you why the port is behaving the way it is. I want to go over something that we need to talk about. I don't know if it gets talked about enough. I think there's a small blurb in the book, but it's VLAN pruning. And just because a switch has a VLAN doesn't mean every trunk should carry that VLAN. In a lab, it is easy to allow all VLANs everywhere, but in a real network, that can get messy real quick. Some environments have dozens or even hundreds of VLANs, and with spanning tree and rapid spanning tree, every VLAN can have its own spanning tree instance. So that means every VLAN you carry across the trunk is another VLAN that is participating in spanning tree on that link. Now, yes, per VLAN spanning tree does separate the topology per VLAN. So a problem in VLAN 10 is logically separate from VLAN 20. But here's the caveat, or here's the real world catch. If the switch itself, let's say the switch itself still has limited resources, right? CPU isn't unlimited, memory isn't unlimited, the control plane processing is not unlimited. And if one VLAN gets caught in a broadcast storm, that storm can consume the switch resources and affect the entire device. So, even if a loop starts in one VLAN, the pain may not stay perfectly contained. The switch will get overwhelmed, other VLANs will start to feel it, users will start complaining, and suddenly everyone is asking, why is the network slow? That's why pruning matters. If VLAN 10 does not need to cross a trunk, just don't allow VLAN 30 on that trunk. Same thing with the printer VLAN, same thing with the camera VLAN. Keep the layer 2 footprint small. What that really does is it just reduces the blast radius of potential problems, right? Carry only what you need. So what I'm saying is, on switch 8, if you only need VLAN 10 and 20 because 10's your users, and I might be mixing them up now, this is the page before, but VLAN 20 could be your printers, right? Now, you only need users to print, so they can print. Cool. Let's say you had VLAN 30 on switch A, and it traversed both switches. Now, say you didn't need it there because you only had cameras on switch B because it's in maybe the bottom floor of a building or something like that. Someone creates a loop on VLAN 30. Eventually, the network's going to slow down, right? But if you contain that traffic to VLAN 30 and switch B, users and the printers on switch A might still continue working like they don't know any different, because the VLAN 30 is separated. Now, that's just a quick, easy explanation. Other things you would probably notice in other ways, shapes, or forms, but for now, that's the general concept of why we want to prune our VLANs and keep them separate if possible. Not always possible. I've seen, trunk links with 10, 15 different VLANs just because you had no choice. But we do our best. That's all we can do. Another thing to watch for is trunk consistency. On an 802.1q trunk, both sides need to agree. You want to verify the native VLAN, the allowed VLAN list, and which VLANs are actually forwarding. If one side of a trunk allows VLAN 10 and 20, but the other side only allows VLAN 10, you're going to have problems. If the native VLAN doesn't match, you can get ugly behavior. So, when troubleshooting spanning tree, don't just simply look at spanning tree as the very first problem, right? You got to check the trunk links, because spanning tree depends on layer 2 topology actually being what you think it is. All that being said, with trunk links is, don't just look at the one switch, right? Look at the other end. If it's going to the core, if it's going to another switch, you gotta verify both sides are up. native VLAN matches both sides. At this point, you might be asking, if we have two links, why not just use both at the same time? And the answer is you can, but not as two independent layer 2 links. If you want both physical links to forward together, you have to bundle them with something like Ether channel. With LACP, multiple physical links can become one logical port channel. Spanning tree then sees the port channel as one logical interface. That means the links can share traffic without creating a layer 2 loop. But if you just plug in two separate switch to switch links and let them both forward independently, that will create a loop. So the rule is, two links by themselves can be dangerous. Two links properly bundled as Ether channel can be useful. That is a separate topic, and honestly, I will make a whole nother set of videos all around bundling ports, Ether channel, and stuff like that. But it does have to be brought up during, a spanning tree conversation. I actually wrote down, put them in Notepad, all the different commands that I've used while trying to, jot a bunch of notes down for this video. I'll make it pretty, and I'll put it, maybe I'll, even make like a cheat sheet of all the commands, and I can post that in Google Docs and attach it to the description of the video. So if you do want that, go ahead and take a peek. I guess we're gonna wrap this up. So let me just reiterate a couple things. Per VLAN spanning tree, or PVST plus, literally just means per VLAN spanning tree. Same thing with rapid spanning tree, or rapid PVST plus, just rapid per VLAN spanning tree. Both allow Cisco switches to maintain a separate spanning tree topology. That means VLAN 10 can have its own root bridge and one forwarding path. VLAN 20 can have its own root bridge and its own forwarding path. In our lab, switch A was root for VLAN 10 and switch B was root for VLAN 20. That shows how the same physical topology can support different logical layer 2 topologies. We also talked about why root bridge placement matters. If a server or important resources live near switch A, then maybe switch A should be the root for that VLAN. That keeps that layer 2 path more intentional. We also talked about VLAN pruning. Do not carry every VLAN across everywhere just because you can. It will bite you in the end. Only allow VLANs that actually need to cross that trunk to allow it to cross that trunk. That reduces unnecessary traffic, reduces complexity, and limits the blast radius if something goes sideways. And finally, we demonstrated why a blocked or discarding port is not wasted. It's just a backup path. It's sitting there waiting for a failure. It's weird that normally you want your networks to stay up all the time, but I bet you that one path is just like, please go down so I can do something. And hopefully it never happens, but if it does, hopefully you can just converge real quick. In episode 1, we saw how one cable can create a loop on one switch. In episode 2, we saw how multiple switches and multiple VLANs make spanning tree more powerful, but also with more important things to understand. In episode 3, we're going to take this to a more realistic network design. We will talk about core switches, access switches, redundant uplinks, bridge priorities, root ports, path costs, and why you do not want some random closet switch becoming the root bridge for your network. Welcome to the panic room, where one blocked port may be the only thing standing between a normal workday and a very angry phone call. Peace for now.